Hello there, I am Pankaj Bishnoi, Applications Director for Everspin Technologies. Everspin is a leading-edge company designing, manufacturing, and commercially shipping discrete and embedded magneto-resistive random access memory, known as MRAM. It has recently launched a higher density spin torque MRAM devices, also known as STT-MRAM. These devices have ST-DDR interface, which is very similar to well-known DDR3 and DDR4 industry standard interfaces. MRAM is a special type of memory device which can be accessed just like any other random access memory, but the data is not lost even if power is removed. It is a persistent memory device which operates at performance levels of SRAM and DRAM, but does not require any capacitors, supercaps, or battery to protect data from power loss. The MRAM memory cell technology is inherently non-volatile. In addition, the endurance level of STT-MRAM is in billions of access cycles. MRAM is instrumental in applications where data persistence and data integrity with high performance, low latency, and security are paramount. By using it as a write buffer in front of NAND flash, it supercharges the storage performance and endurance. And by using it alongside volatile DRAM, it can provide power loss protected burst buffers to greatly increase write performance without requiring any batteries or supercapacitors. To make it super easy for developers to use STT-MRAM technology in their applications, we have launched a Storage Accelerator product with our partner, Smart Modular Technologies. It is called nvNITRO, which is NVMe compliant device available in half height, half length PCIe by 8 card, as well as U.2 form factors. It boasts industry-leading performance with less than 7 microsecond latency at queue depth of 1, over 6 gigabytes per second throughput, and 1.5 million IOPS for 4 kilobyte blocks with 100% random write data patterns. Today, I'm going to share with you how to leverage this power loss protected data performance in an NVMe over Fabric setup over a 100 gigabit RDMA network. Let's first look at the entire setup. Here are the two servers which will be used to demonstrate NVMe over Fabric setup with nvNITRO. This server with nvNITRO plugged in will serve as a target for NVMe setup. And this one on my right will be the initiator without nvNITRO. Let's take a closer look. NVMe over Fabric extends the same benefits of NVMe storage in a local application server over to remote systems over RDMA networks. It also provides a more efficient data path with low latency and higher performance. Both the servers have very similar hardware and software specifications, except that the target server definitely has nvNITRO plugged in, but the initiator does not. For this demo, we are using a KVM to share the resources between the two servers, the initiator and the target. You can see the KVM sitting behind the monitor. This is the target server. It has the nvNITRO card plugged in, as well as a Mellanox ConnectX-5 100 gig VPI card also plugged in next to it. This is the initiator for NVMe over Fabric. As you can see, this has only Mellanox ConnectX-5 adapter card plugged in, and they are both connected through this InfiniBand 100 gig cable. The two servers are connected over a 100 gigabit RDMA network using Mellanox ConnectX-5 adapters. You can see here that we have a back-to-back direct connection between the two systems without using a switch. This is a quick way to demo NVMe Over Fabric, but we are limited to active state on only one of the ports. In this case, we are using IB1 as the port. Let's look at the target server and familiarize ourselves with the desktop widgets quickly. Here on the top right is a widget showing CPU and memory resources used by active processes right here. On the bottom right, we have CPU utilization. This is a 4-core single socket server with hyper-threading. Hence, you can see 8 cores active over here. Both the initiator and the target have identical desktop widgets. The name on the desktop identifies whether we are on target or initiator system. To confirm we have an nvNITRO plugged into the system, let's list block devices on this target server. Here you can see all the block devices listed, but really of interest are these two, disk over here and the disk over here. Rest are partitions. The first disk which we have over here, NVMe 1N1, is our operating system disk. This is where all our programs and everything are stored. NVMe 0N1, this is a 1 gigabyte disk. This is the nvNITRO disk. This is the SSD NVMe drive which we will be using as a NVMe target. Definitely note the address NVMe 0 and 1 which we will be using later on. You can also go into the Centos GUI to cross-check here. You can look at there is this 512 gigabyte disk which is our OS disk, and you can see all the operating system partitions over here for the Linux, and this is our NVMe nvNITRO drive. Again, over here you can look at the device assigned to nvNITRO. It's /dev/NVMe 0N1. Next, let's ensure that we have the Mellanox ConnectX device under network settings. Here you can see that for physical IB port 1 of the InfiniBand VPI card, it has IP address of 1.1.1.1 assigned to it. This will be our NVMe target IP address. You can see the other port 0 is disconnected. Let's switch over to the NVMe initiator system now. As you can see, the desktop is identical to the target system except the desktop name, which shows NVMe Initiator. To verify that we do not have any nvNITRO plugged into the system, let's list the block devices on this system also. Here you can see there is only one disk available, NVMe 0 and 1. That is the operating system disk for Linux. There is no other 1 gigabyte NVMe nvNITRO present over here. All of the other ones over here are the partitions for this NVMe 0 and 1. You can also go into the system tools or utilities and look at the disk. There is only one device present, 512 GB disk. Rest of them you can see are CentOS partitions for root, swap and home. As you can see that there was no nvNITRO present in this Initiator system. Next, let's ensure that we have the ConnectX device under network settings. Here again, there is no other network devices connected, except that when we go to InfiniBand IB port 1, we see an IP address of 1.1.1.2 assigned to it. This is the Initiator IP address we'll be using for NVMe Over Fabric setup. An orange LED in the back of ConnectX cards, which is lit up. This is because the ports are in the init state and not active yet. Since the servers are connected directly without a switch, we need to run a subnet manager on one of them to bring the ports to active state. We will do that later as part of our automatic NVMe target script. It's time to go back to the target system and check a quick performance of nvNITRO local to that system. This is going to be insightful because we can understand the impact of the fabric when we access that device over the RDMA fabric. Now we are back in the target system, as you can see from the desktop name over here. We'll be using industry standard FIO test to do a quick performance test on nvNITRO. To make it easy to visualize the data, we will use GFIO, which is a graphical tool that calls FIO in the background. Before we start the test, let's look at the FIO script that we'll be using. First one is a FIO test for finding throughput, that is bandwidth and IOPS performance using this script. There are three sections. The first one is just a global setup, just highlighting how many CPUs are going to be used for this test. The file name is basically the device we are using as a block device, which is our nvNITRO as we saw earlier, NVMe 0 and 1. Now we do some of the basic preconditioning by just filling up the drive. Since it's 1 GB Storage Accelerator, we just run it for 2 seconds and it goes ahead and fills up the drive. And the last block over here is the random write test, which we are going to be running on our device, which is nvNITRO. We wait for some time till the preconditioning is done, then we run the test. But for this demo, we're just going to run it for a short while and look at the performance numbers. Here we are using a block size of 4K, IO depth or queue depth of 8 for 8 queues or 8 jobs. This is a 100% random write data pattern. So let's get started. We have already written a demo shell script which will start the GFIO. Here you notice this graphical user interface for running FIO tests. Let's open our random write test with the script, which is randomwrite.fio. Set up the configuration. Make sure we are connecting over local socket. Send OK. Now we connect to the test over the local socket. For FIO, we send up parameters for the test. You can see there are 2 jobs, sequential fill and the random write. First is going to run the sequential fill and then it'll go ahead and start running the random write test. So let's go ahead and start. You can see over here, after 4 seconds, starts the ramp, and within the 5th second, it has started running the random write test. Before that, it was doing the preconditioning. As you can see, that nvNITRO is showing industry-leading benchmark results here with 6 gigabytes per second throughput and about 1.5 million IOPS. Also check out how all the cores of the CPU are busy feeding nvNITRO with jobs. All the cores are fully occupied. I want to mention that we also have a screen recorder running in the background which may steal some CPU cycles. If this was a higher end server system, you may even see higher throughput and IOPS. Now we run FIO script to test random write latency for nvNITRO device. So this script is pretty similar to the previous script, but the key difference over here is this test is going to be run for IO depth of 1 or Q depth of 1. One job is going to be spawned off and only one core of the CPU is going to be used. This is going to be a very good way to see how a single Q depth application would perform. Let's go ahead and connect to this test, send the parameters, and you can see we have the latency write test over here, and let's go ahead and start the job. Similarly, you can see that there is a ramp up time, and right now you can see that all the other CPUs are not active except for CPU 1. All the other CPUs are not really sending any jobs. Only the first CPU. After running this test for some time, we look at the results. Let's go ahead and disconnect the test. Now over here, you're going to see the test results. Let's go to the tab where we ran the random write test. You can see over here our average write completion latencies is around 5.9 microsecond. Our total latency from end to end is about 7.5 microsecond with a standard deviation of only 23 microseconds. We can see for this latency job run, the average completion latency is very low. And also the standard deviation is extremely small. Latency distribution for 99.9% samples is within 37 microsecond. This is a latency distribution curve with virtually no tail. This shows a very deterministic latency response result, which is excellent for latency sensitive applications. As you saw here, that nvNITRO performance for local machine on this system is unmatched in industry. Let's now move on to configure the NVMe Over Fabric setup on this target system. I have already written a script to automate the steps to set up NVMe target system. Let's look at this script. So here is the script which we'll be using for configuring the NVMe target. The script is called nvme_target.sh. First, we are running the subnet manager to bring ConnectX InfiniBand cards to active state so that the connection can be established between the two systems. Right here is the service which we start for subnet manager. Then we insert the NVMe target core and RDMA kernel driver modules. You can see them here. Then we create a new subsystem for NVMe target. You can call it anything. We are calling it NSES1. Then we allow any host to get access to this target. We also create a namespace associated with our subsystem. Here we call this ID as 1. We also have to ensure that we program in the nvNITRO device information in the device path. Our device is NVMe 0 and 1, so we set it up. Then we enable the namespace. Now we go ahead and set up the NVMe target port with associated properties. You can see over here we have used our target IP address of 1.1.1.1 and we are using the port 4420. RDMA is the type of transport we are going to be using. It is also very important to note that we have to provide access to this port 4420 through the firewall. So we have to go and set up the firewall to allow access to TCP and UDP ports for 4420. You can go and do that through firewall settings in CentOS like this. You have to go into the permanent configuration so that when you boot next time, it's going to be still set up the right way. Here you can see 4420 TCP and UDP ports we have added to allow access through. And we have to do that for both the initiator and the target system. Alright, let's get back. Now the final step, we have to enable the NVMe target port by creating a soft link. If everything went fine, we should see a kernel message verifying the status. We can grep on the kernel messages, which is dmessage log file for NVMe. Let's try that. Well, obviously we have not run the script yet, so we didn't see anything happen here. Let's go ahead and run the script. And the script ran without any errors. So now let's go ahead and grep on the D message again. Now you can see over here that we had the NVMe target setup. It added NSID1, namespace ID1 to subsystem NSES1. And for the RDMA, it enabled the IP address on port 4420. Great, we are done with the NVMe target setup. NVMe target should be ready at this point to accept host connections over the RDMA fabric. Let's move over to the initiator system to set it up for target connection so that it can access our nvNITRO device over RDMA fabric. I have already written the NVMe initiator script to make it easy to make a connection to the target device. Let's first make sure that we do not see that drive on the system yet. As you can see, there is still only one disk which is physically present in this initiator system, which is NVMe 0 and 1. We do not see any other disk, only partitions. Let's go ahead and look at the script. So here, first we load the kernel modules for Mellanox InfiniBand device and then NVMe RDMA. Before you can access utility command NVMe discover or connect, you need to make sure you have NVMe CLI installed in your system. This is important to discover and connect to NVMe target subsystem. You may have to download the source and compile it on your system. Now, let's make sure this device does not exist in the system. We cross-checked that there is no nvNITRO device on this system. Let's run the script. We are going to run the NVMe client script, which will discover and connect to the subsystem on the target. And here we see that it was successful. We look at the discovery. It did discover an NVMe subsystem on 1.1.1 IP address, because we had already specified on discovery, we had provided an IP address of 1.1.1 and a port address of 4420, and then we had requested to connect. So it did find the NVMe subsystem on that port and on that IP address, and then it was successful in connecting over the RDMA transport. What we should see now, when we list the block devices, a new device has been created. A new NVMe device has been created. Here now we see NVMe 1N1 is a new NVMe device which was created on the system. This is actually our same nvNITRO which is in the target system. We have successfully now mapped an NVMe device from the target system over to the initiator system over an RDMA fabric. We should be able to see the same device under the disk. And here now we see this NVMe device 1N1, which is present on the target, now mapped onto our initiator system. We can now run FIO tests on this device as if it belonged to NVMe Initiator, even though it's not physically present in the system. We're actually running the FIO test over the RDMA fabric on the target system's nvNITRO. So let's start with running the bandwidth and IOPS test with FIO and use the same 100% random write data patterns. Let's go to the FIO directory, check the file we are going to run, FIO script, which we are going to be running with GFIO. Here you can see it's a similar script like earlier, except that our device number is now 1N1. And this is the same device which we saw earlier is our device mapped over NVMe fabric. 1N1 is 1 GB nvNITRO. And we are going to be running same queue depth of 8 with 8 queues or 8 jobs for random write patterns, 4K block sizes. All right, let's try to run this test. Let's connect to the test. Send the test parameters. Here we can see we have a random write test, and before that we have the preconditioning. We start the job. What we see here is the impact of the fabric, the limitation factors of the network card, which is in between the two systems, but still we are getting about 5 gigabytes per second over this fabric with 100% random write patterns, and with IOPS of 1.2, somewhere between 1.2 to 1.3 million IOPS. We can see over here on the CPU widget display that all the CPU cores are 100% busy. Possibly with a better server system with more cores as well as better processing capabilities, we will see much higher throughput. What we are seeing here is best throughput and IOPS performance in the industry. Let's go ahead and disconnect this test and run a latency test over the NVMe Fabric. Let's check out the script which we are going to be using for the latency test. Here again, we are using NVMe 1N1, and we are going to run it for queue depth of 1. Only one job is going to be executed on one CPU core. Let's go ahead and load this test. Let's connect, send the test parameters, and start the random read latency test job. As we can see here, we have a preconditioning with a ramp up for our test. On the right hand side on the CPU display, we can see that all the other cores have become silent except for the first core. So now let's look at what the latency numbers look like over NVMe Fabric. Let's go to the tab for random read latency. What we see here is a completion latencies of 15 microsecond over the entire NVMe Fabric. The total latency end to end is 17 microsecond. When we look at 99.9% latency distribution, we see a max of 40 microsecond over NVMe Fabric. As you could see that nvNITRO offers an industry-leading performance for bandwidth, IOPS, and latency for any type of data patterns, whether it is in the local system or NVMe over RDMA Fabric. Folks, today we saw how MRAM-based nvNITRO Storage Accelerator can be used as an NVMe target on RDMA network for extremely high performance and low latency storage traffic. You could imagine an NVMe over Fabric storage array where the entire array of drives is front-ended by nvNITRO as a circular write buffer, which not only keeps the data protected from power interruptions, but also provides ultra-low latency and high throughput on writes. With CMB buffers on nvNITRO and NVMe offload available in ConnectX-5 and ConnectX-6, you can further reduce the latency by about 7 microseconds. I hope you enjoyed this session. Thank you for your time. Goodbye.